Hello everyone, welcome to a new video, and today in this video we are going to discuss about the steering factor in case of an steering factor equation of an antenna, of a base station antenna or transmitting antenna or receiving antenna. So the question is, when a wave travels from a source to an antenna elements, then the question is, does the same wave does the value, the magnitude or the phase of the wave remains the same for all the antenna elements? So suppose you may not able to relate what I am saying. Suppose this is our source and this is our antenna. Okay, now suppose the signal receives here and the signal is received here. Can you see me? Signal is received here and signal is received here. Now thus the value of the signal received at the first element of the base station antenna. So these bars are the antenna elements. So the signal received at the first element of the base station antenna element is the same value of the signal gets traveled to the nth antenna element. That is our question. So if we going to see like geometrically, it should not be right, because if we see, there is a difference of the distance here is d is nt minus 1. So there is a distance of nt minus 1, so that will be get counted. So if we see what I am going to say, that when a plane wave arrives at an angle theta, then each antenna element receives the wave at some extra time delay. Obviously, if you think also in general terms, suppose in some microseconds delay will be there, right? The signal that is get received in the first element and the signal is from the same source, but it's getting received in the nth element. There will be some amount of delay, and that delay is tau equal to d sine theta by c, where d is equal to lambda by 2. Also what I want to say here is that, wait, whenever there is the base station antenna, so these are the antenna elements. So the distance between the antenna element is spaced generally in a spacing of kept in the spacing of lambda by 2. So from there the term distance d equal to lambda by 2 term comes. Now you may have the question that from where the sine theta term comes. So let me explain it properly. Okay, see, in a zoom way, if we zoom this, say suppose these are my antenna element. This is the first antenna element, second antenna element, and mth antenna element. Then distance between each antenna element is lambda by 2. Okay, suppose let us assume that this is our source ray. This is suppose a big source. The source ray hits antenna element 1 at an angle of phi. Okay, so geometrically, if this angle is phi, so this angle will also be phi, right? Then if we take a right angle from here, obviously it will be right angle, because see, this is vertical, the ray will hit here, then this angle will be 90 degree. Then if this angle is also phi, geometrically, if this is phi, then this will also be phi, because these are all right angles. Then this angle will be 90 degree minus phi. Okay, so if we want to find the distance between the ray hitting point, see, I will explain some other point. This is the point where the ray hit in the first element, and this is the point where the ray hit the second element. So there is a distance, this is some amount of distance, right? So from here we got to know that this distance will be the total vertical distance. Okay, means this hypotenuse distance, the hypotenuse we calculated as m minus 1. Okay, then the distance del, then cos theta, cos of this angle. Okay, so this cos theta will be this. Okay, so this cos of 90 degree minus phi, because this angle will be 90 degree minus phi, so the distance will be m minus 1 del sin phi. So distance we got to know. If we know the distance, then the time taken or the delay in receiving the ray between this point and this point will be, so geometrically will be m minus 1 sin phi by c, or m minus 1 is also represented here by d, that is the same thing. So we found that tau is d sin phi by c. Now you will ask me that what we will do with the delay. Okay, so from the delay, so we got to know we can find the phase shift from between this element and this element. So in time domain, the delay will be in some kind of millisecond or microsecond say, and from there we will find the phase shift. So how we can find the phase shift? Phase shift is 2 pi f c tau, and fc is the frequency of the light coming, means frequency at which the signal is coming. So 2 pi fc into tau will be d sin theta by c. So 2 pi fc, then d is by design in generally we take it as lambda by 2. So 2 pi fc lambda by 2 sin theta by c. So from there we got the term that there is a phase shift of pi sin theta between each element. So if these are the, I will show you, these are the elements. Okay, element number 1, element number 2, element number 3, and element number nt, or these are the antenna elements in a base station, in a transmitter, or in a receiver. So there will be a phase shift between each element of pi sin theta. So that only we are going to trying to say. See, so the nth element, so their elements are 0, 1, nt minus 1, receives a signal with phase delay of n pi sin theta. So the last element, if there are total n element, as if the nt element, the nth element okay, will receive with a phase delay of n pi sin theta relative to the antenna 0th antenna element, that we are going to see. So if we know the phase, so then we can write the, we know the some kind of then the received signal will have some kind of attenuation. Okay, and also we will have some kind of phase difference, and we calculated the phase difference. So the phase difference we just now calculated as e to the power minus j n pi sin theta. Okay, so that is only our steering vector, that is the steering factor we are talking about. This collection of the amplitude, and suppose by for our simplicity we have considered the attenuation to be 1. Suppose for all the antenna elements the attenuation is considered to be 1, then the steering factor is the collection of the phase differences of all the antenna elements in the transmitter or the receiver. For that transmitter or the receiver, it can be base station, it can be a RIS element, it can be a receiver. So there can be steering factor for different things. So like this, that is called the steering factor. Steering factor is the collection of the amplitude and the phases of among the different antenna elements of a base station or transmitter or a receiver. So I hope you all understood. So that's all.